Hi, I'm Juha, CEO and co-founder of QuantScient. In this webinar, you'll learn about QuantScient AllSolve, our cloud-based finite element method multiphysics simulations platform. You'll see the quite literally unforeseen advantages that QuantScient AllSolve can deliver in terms of speed, scalability, and flexibility. You'll learn how to simulate a multiphysics simulation involving piezoelectrics, acoustics, and solid mechanics with over 20 million unknowns in less than 5 minutes. You'll even learn how to run many of these in parallel. I'll now hand over to Dr. Alexander Halbach, our CTO, to dive deeper into the simulations. Have fun watching the webinar. Thank you.
Thank you, Juha. Yes, indeed. We will explore first how to make a very simple eigenmode analysis of a mechanical piece, just to give an idea of how the workflow is in the product. And then as a second step, we'll move directly to the multiphysics simulation of an ultrasound transducer, a single one to start with, and then we'll run a really large scale simulations of more than 20 million unknowns within just 2-3 minutes in the last of the 3 demos. So hang on, and we're gonna get there very quickly. Let's start immediately with the first simulation, that is the mechanics simulation, just to get you introduced to the tool. So how does this work? You have your browser in front of you. You connect to this website. If you want to share a project, you just send the URL to that website to anyone who has access. You have a bunch of demo projects that are waiting for you. You can copy them and start from there. And otherwise, well, you understand it. You don't have to install anything, and it's just running on any platform very conveniently. What we're going to do now is to create a project. We will call it eigemnode analysis of a cooling blade. And then from there, you can either draw simple shapes or import a step file, which is what we're going to do. Here are cooling blades from a commercial cooler. Of course, you can import other formats like GDS formats that are really targeted towards semiconductor industry and MEMS devices for ultrasound transmission. But here, this is our cooler, so we can defeature it a bit the way we want. We can also, as said, draw simple shapes or edit it in several ways. Here, I will just remove the outer shell just to see how the blade vibrates. So this is all we have to do. And we are left with only the center part and the blade. If we do an eigenmode analysis on this, we expect to have couples of 5 clusters of resonance frequencies at around the same frequencies, because they will correspond to each to one of the blades in one of the vibration modes of the blade. And this is what we're going to investigate right now. So we can add materials in the next part of the setup. So a bunch of predefined materials are waiting for you. Some, for example, very useful for MEMS devices like monocrystalline silicon with all the material properties anisotropic as needed and with the crystal orientation as needed, or other types of materials like, for example, here, aluminum. So let's just pick the aluminum. And what we could say here to keep things simple is that the entire blade is made out of aluminum. At any point, of course, you can edit the properties. You can make things anisotropic the way you want. You can make things temperature dependent just by multiplying by capital T, for example, or you can import CSV files of measured experimental data that you might have very conveniently. But here, let's just use aluminum for the first demo. This is all set. Then we go to the physics, where we can highlight the vast range of physics we support, from any types of waves, so elastic wave, electromagnetic waves, acoustic waves, of course, any kind of coupling. So if I'm going to add solid mechanics and acoustic waves, then suddenly you see acoustic structure interaction appears, and suddenly you do acoustic structure vibration interaction. But any other physics, for example, also magnetics, thermal cooling, and other CFD physics. So you're really covered in the range we're providing. Here, it's going to be eigenmode analysis for linear solid mechanics piece. So we select the solid mechanics piece, physics, and we want to set some boundary conditions. Here again, a lot of different boundary conditions. and also the piezoelectric material coupling, for example, if you want to couple the electrostatics or the current flow to the solid mechanics. Here we're just going to use the clamp, and we will say that we just want to investigate what is the vibration of the blade. So we will kind of shake the blade and not be interested in the central part, but just on how the blades vibrate. So we'll clamp the top and the bottom. That's it. Nothing else to define for this eigenmode analysis. We can jump to the simulations, and there you can run any number of simulations at the same time of totally different kinds. They will really run at the same time. If you want to run sweeps with 100 different values for a given parameter, then you just define a sweeping variable and you will get 100x speed up for large scale simulations. It's as easy as picking a sweeping variable and saying what values this variable should take. In this case, we're just going to run a single eigenmode analysis. So we choose the eigenmodes analysis type, and we will say, for example, that we want the first 8 eigenmodes centered around 0 Hertz. So the first 8 eigen frequencies, resonance frequencies. And then we might want to see as output the eigenvalues or the mechanical displacement. So what we do first is meshing. So lots of options for meshing. Here it's a simple geometry, so we can just use the default meshing options. But we can mesh any kind of complicated geometry. So we need to run the mesher, and then in just a second we can investigate how the mesh looks. There we go. So we can show the mesh preview, and it looks really decent for the application we are targeting. Now we can run the simulation. If we want to run a simulation with 100 nodes, each of them with 32 gigabytes and 512 gigabytes of RAM and 32 cores, then it's as simple as this. There's nothing else to change. Here, it's a fairly simple simulation, so we'll just use the defaults. So now we can press run. And while it's running, I can highlight the scripting feature we can provide. So here's the entirely automatically generated script, high-level Python finite element interface that is automatically generated for you based on what you have done graphically. If you want the full flexibility to do whatever you want and automate whatever you want, you can at any time go to this scripting interface, but you don't have to. Here, we're not going to change anything, and we will just use the graphical interface. And we can check the status of the simulations here in the logs, and it seems it is now showing the eigen frequencies. So as expected, we can see the first cluster of 5 very similar eigen frequencies, which correspond to the first vibration mode of each of the 5 blades, and then another 5 for the second mode, etc. And at any point, you can investigate like the visual results by just clicking and activate the current visualization, and you will be able to see what is the vibration mode of each of the 15 computed resonance frequencies. So unsurprisingly here for one blade, although all these first 5 modes are clustered really close by in terms of resonance frequency, this is the first vibration mode for the first blade, and then the first 5, unsurprisingly, will be corresponding each to another blade. And if we want to investigate how the last mode looks like, then it will be likely the third vibration mode of the blades. So this is it. And we will now jump to the next simulation, where, as said, we will investigate how to set up a PMUT, piezoelectric micro machine ultrasound transducer. So it's a multiphysic simulation of a vibrating micromembrane that emits ultrasound in the ultrasound range. So like from anything from 40 kilohertz to megahertz acoustic frequencies. After this, we will go for the large-scale simulation of a 15 by 15 array with more than 20 million unknowns. And you will see this just runs, even for sweeps of several frequencies, you can get these 20 million unknown runs for 10 frequencies all together within 2 to 3 minutes. So hang on, let's start right now with the PMUT simulation with one single PMUT cell. So this single PMUT cell vibration. So let me remind first, what is a PMUT? A PMUT is a micromembrane, in this case made of silicon, that vibrates thanks to a cavity that is etched below. And then on top of this, there's a layer here of PZT, piezoelectric material, sandwiched between two electrodes. And as the electrodes are driven with an AC voltage, you shrink and you expand the piezoelectric material, and this brings the cell to typically resonance frequency, and this emits or receives ultrasound between anything, typically between 40 kilohertz to 10 megahertz of resonance frequencies for, I think here it's a 100 micrometer diameter device, if I'm not mistaken. So the geometry here has been fully drawn in the graphical interface. Of course, if you have a GDS or step file, it's just a drag and drop operation. So let's define first something we want to sweep on. If you just want to see the vibration at one frequency, you don't have to do this. But if you want to sweep over a frequency range and run all these frequencies at the same time to get, for example, 10x speed up by running 10 different frequency simulation at the same time, then you define this shared expression. The next step is to assign materials. So we have air here on top, very easy. We can hide the top part so that we can easily access what's below. What do we have otherwise? We have monocrystalline silicon. So this is everything that hasn't been etched away around the cavity. So this is monocrystalline silicon, but also this and this. And then, so this is the standard wafer orientation. It's anisotropic. What do we have on top of that? We have PZT here predefined. You can again investigate all the properties and rotate the crystals and whatnot. Here it's also anisotropic. You can change anything here, but we will keep the default values. All right, so it's saying I'm missing a target region. So what do I need to do? I need to indeed select that this is the PZT region. So that's it. These are our three materials. We can jump to the next session. What do we need for, in terms of physics, for this three physics, solid mechanics, electrostatic, acoustic simulation? Well, we need indeed this solid mechanics, electrostatics, and acoustic waves. So that's it. Solid mechanics, where would it be defined? Well, not in the air, but everywhere else. So I can say that it's defined everywhere on all the visible parts here, because I've already unselected the air. And indeed, then everything is picked except the air. So this is fine for the solid mechanics. Now, in terms of electrostatic, well, we could assume that we only compute it in the PZT layer here. Then this is it. And then obviously the acoustic wave, this only happens in the air layer. So now my three physics are defined at the right places, and I need to set up the boundary conditions. So for mechanics, again, I can hide the air for convenience. For solid mechanics, I will want to, for example, clamp the bottom surface. So this is it. What else do I want to do? I also want to say that I have a piezoelectric behavior in the PZT material. So I will use this multiphysics coupling, and I will say that this happens in the piezoelectric material. Now, the electrostatics will induce stresses in the mechanics, and the mechanics will induce charges in the electrostatics in a strongly coupled way. So this is all we need to define for the solid mechanics. Now, in terms of electrostatics, we need to drive the electrode. So I could hide all but the PZT layer for convenience. And then I can assign a ground electrode, for example, at the bottom here. So this is going to be grounded, 0 volts. And I can assign, for example, another forced voltage on the top electrode. And this will be driven at the driving frequency for harmonic analysis with the real part only. So this is it. And then the last step is simply to add the acoustic waves definition. So what do we want? We want to let the waves go out because we just truncate artificially the air domain, but we want to let all the waves flow out. So for that, the best you can do is use a perfectly matched layer. And here it's very trivial to set up. So you just pick the surface all around and everything will happen under the hood. So the structured mesh extrusion optimally done will just happen under the hood in an optimal way and totally automatically. So that's all you have to do to define a perfectly matched layer for any type of wave equation. Other thing we are missing, the last thing we're missing is the acoustic structure interface. So you just select that. It knows where the air is. It knows where the mechanics is. This is going to be added at the intersection of the acoustic and the solid mechanics region. And now we are done. Everything is set up. We can move to the last step, the simulation phase. Again, run any number of simulations at the same time. But here we're going to do one harmonic analysis of this linear system. If you want to do a harmonic analysis of a nonlinear system, then you're going to choose this option. What are we going to drive it with? Well, we have defined this variable frequency. We can use this, or better, we could make a sweep over several frequencies. And if we do this, then what we could ask, for example, is that we want to run not only for one, but for several frequencies at the same time. So for 1 megahertz, 1.5 megahertz, and 2 megahertz. So these 3 runs will be done at the same time. Whatever the size of the simulation here, for big simulations, you're certain to get 3x speed up. And this is on top of the usual speed ups we provide. So I didn't say this, so let me set it again. So we're going to drive with the frequency that is used for the sweep. And that's all we need to do. This is not a large simulation, but nevertheless, we don't want to wait 10 minutes. So we're going to use 20 nodes of each one core to speed up a bit the simulation. And what do we want to see out? We might want to see very likely the pressure, for example, the real part of the pressure. And of course, also we're interested to see in how the membrane vibrates, so the displacement. That's it. Next step, as usual, let's mesh. For here, we could use the default settings, or we could explore a bit what's available in these expert settings. Lots of options. I could just highlight 2 if you want to refine the entire mesh versus the initial coarsest possible mesh that is automatically created for you. Then you could refine in all directions by a factor 2. You could also capture the curvature of the cells a bit better. And you have lots of options you can refine at given volumes and whatnot. So this just here highlights two ways to tune the mesh. Again, I need to highlight this feature we have, that is the automatically generated script. So here we have 3 physics strongly coupled, and this is the Python high-level Python interface to our finite element code that we're running. If you want to edit it, you go to scripting mode and you see it's fairly concise. It's just 87 lines of code for these 3 physics strongly coupled. So really ideal for tunability and flexibility. This is really removing all the boundaries that might be brought on you by a graphical interface. But again, you don't have to use it. We're not going to use it here. We can inspect what the mesh looks like as usual, and then we can as well run the simulation. Here, what's going to happen when I start running is that 3 runs for 3 different frequencies will be executed at the same time, and each of them will have 20 nodes. So these highlight again the 2 ways to accelerate simulations. First, accelerate each run dramatically, here by more than 20x. And second, run several heavy simulations at the same time. So really ideal for these heavy computations. Now, we obviously don't want to waste your time, so we accelerated this video and we will jump immediately to the results. So here are the logs. The 3 jobs have been running at the same time, and each of them you can find the logs here. So you can see that we have run on 20 nodes in 20 pieces. We have partitioned the mesh. You can see that the total runtime for these 1.2 million unknown simulation with a single cell was 24 seconds. And this involves 3 physics strongly coupled together. The whole runtime was about 24 seconds as well, because all these jobs have been running at the same time. Now we can also visualize the results. We could visualize, for example, how the membranes vibrate. Here, the single membrane vibrates. And then we can also overlay the pressure field on top of that. So here, the PMUT vibration, you can do lots of things like warping it and whatnot. You can also overlay the pressure field, or just show the pressure field, and you can show that for all the 3 simulations that you've been running. You can make cuts. So if we're going to make a slice, then simply, well, you define where your slice is, and there we go. You just render the slice, and here you have your slice. And then you can also see how it changes from one run to the other one. All right, so this was for a single PMUT's membrane. Now, what if we would run 225 of them? That's a 15 by 15 array. This is obviously going to be much heavier, because now we had 1.2 million unknowns. Now with 225 of them, we're going to be much higher, north of 20 million unknowns. So this is what's going to come right now in this third simulation. A large-scale 3 physics strongly coupled simulation, all in the browser, and the results you get for several frequency points at the same time. You get all this within 3 minutes runtime. All right, so let's go for the third and last chapter of this simulation video. So the large PMUT array vibration simulation. So here we have the same as just before. So we just don't have one PMUT. We have 225 of them. And here they are. Still the air on top. Each PMUT still is the whole mechanical vibrating device with a piezoelectric layer on top. We can inspect them individually. So here they are. They're all the same, and there's no specific extra assumption made here. It's just brute forcing the simulation. Now, we have run it already, just to save you the time of like setting things up, because there's obviously a bit more things to pick. But the principle is the same. You have your frequency defined here, and you will sweep over this frequency. You have your air domain here, and then you have the monocrystalline silicon membrane everywhere on each of the PMUTs. And then you have the PZT, piezoelectric layer on top of each membrane. Then we go to the physics, and here nothing changes. You have still your PML, the solid mechanics region, the clamps for each of the membrane, the piezoelectric coupling, the electrostatic physics with the piezoelectric coupling, the acoustic waves with the acoustic structure interaction, and again, as usual, really easy to set up perfectly matched layer to let the waves go out. And for this, all you had to do is simply pick the outer surface. Very easy. And then as a last step, you simulate it. So if you want to run a frequency sweep, then this is where it happens. The script is still readable. It's the same script at the same place. And we will get the same outputs. All you have to do is click simulate, and then, well, we saved you this time, but we can check the results in the logs. So you can see that here they have been north of 31 million unknowns. And you can see the simulation converging very quickly and running actually in 222 seconds, which is it's true we have light a little bit. It's actually 3 minutes and 42 seconds. But nevertheless, for 31 million unknowns, 3 minutes and 40 seconds for as many frequencies you would like at the same time. And we can evaluate like visually how the pressure pattern looks, for example, on a given slice. Now the results start to be a bit more significant to render in the browser. So just to keep things quick for you, we can make a slice that will be pretty light render. And there we go. And we will see our pressure field. Now, as you can see here, we have run the simulation not on 20, but on 100 nodes. And this is because, well, this wouldn't run on 20 nodes. So you really need significantly more cores to run this kind of heavy simulations. As the last step, we go to the simulation. We can inspect a cut in the pressure field over all the cells. Here it is, for example. 32 million unknowns, less than 4 minutes. Thank you for watching, and as you have said, we hope to see you all at our booth and talk about this. Make any demo you want, and we hope you